Hi there, in this video we're going to talk a little bit more about continuity and try to give some real life examples. So continuity in practical terms, so say if I climb Mount Lassen, starting at an elevation of 6,000 feet, ending at an elevation of 11,000 feet, must I have passed through an elevation of 8,750 feet? What do we think? Did I have to go through that elevation to go from 6,000 feet? So if you go to the base of the, not the base of the mountain, but at the trailhead to climb the peak is at 6,000 feet. And then you don't quite end up at 11,000. For those of you who may have gone to Lassen and may have done this height, is more like 10,450 something feet. But that's just around over here. So do I have to have passed through that elevation? Hopefully, right? So if I start my hike, so I'm gonna do this little mountain here. I guess I could have kept the same graph, but if I start at 6,000 feet and I start my hike here, and then I make it to 11,000 feet, the peak, then do I have to have crossed 8,750 somewhere along the way? Yes, right, unless I have some sort of teleportation that I can skip going through it. This represents, so this is an example of my hiking path is a continuous path. So I am hiking a continuous trail, and so I have to have passed that. So the elevation is also a continuous function. So then in order to go from 6,000 to 11,000, I have to have passed every value in between. It will be really probably scary to be skipping some elevation values and that's like where those like a black hole happens, right? And then you skip part of it, so you don't want to do that. So hiking, things like this, elevation is a continuous function. So to go from one height to another, you have to pass every value in between, and that's what we know as the intermediate value theorem. So the intermediate value theorem tells us that if we have a continuous function on a closed interval, and L is a number between f of A and f of B, then there's at least one number C in that open interval AB, satisfying that the function value of C is equal to that L. So here, for example, back to my mountain hiking experience, I have my interval is going to be then the time when I started hiking, that will be like my AB, and then my function values are the elevations. So if I start here at a particular time, say I start at 8 a.m., right, and then I end like at, let's say 1 p.m. It's when I reach the top, right? Then that's my interval, 8 to 1. So, and then my hiking, my F of C, right, is 6,000 to 11,000 feet. So my elevation at 8 a.m. is 6,000 feet. My elevation at 1 p.m. was 11,000 feet. So somewhere between 8 a.m. and 1 p.m., I have to have crossed 8,750 because this is a continuous path on my closed interval. Why closed? Well, because if I had something that wasn't a closed interval, so say that I had A and B and my function is only continuous on the open interval AB, right? So if this is my case, so if it's continuous on the open interval AB, do I have to cross 8,750? No, right? So the intermediate value theorem says there is a C such that f of C is equal to L, but I could have L be somewhere outside of that, right? And so then f of C is not going to be in between. So I couldn't claim that f of C has to be L because it could be, f of C could be up there. Right, so then so being continuous on AB, I have to be on closed AB so that then this can't happen. right? If I'm on the closed interval, AB, then those are filled in. And now I have to have it. I have to go between every point in there. Whereas if one of those is open, that gives me freedom to put that value elsewhere. So that is what the intermediate value theorem is telling us. And so if you have an increasing function, this is what it looks like, right? You have your closed interval AB, so it's continuous on the closed interval. Then if there's a L in between them, then there's got to be a C on the axis that gives you that function value. And there could be multiple ones as well. That's what this graph is saying. Another practical application is I'm going to show you this funky looking pancake and see if could we cut it in half. So if this was the last pancake at breakfast morning and you and somebody want to share it and you want to cut it exactly in half, how would you do that? Could you cut it in half? Now this, I know that they may appear symmetric, but they're not. And so how do you find the halfway point? How do you know you have exactly half the pancake? So one way to think about it is imagine that you hold the knife and you start with on the left at 0 and measure the area of the pancake as you go across. So as you start moving the knife, right, at the start of the pancake here at 0, you'll have 0% of the pancake. And then as you get all the way to the right, then if you put the knife here, you will have 100% of the pancake. So, and you're looking for the area as you move your knife from left to right, right? Area to the left of the knife and area to the right of the knife. So assuming that the area is a continuous function, because it is, at some point you're going to have your knife position is going to be somewhere where you have 50% of the area on either side. So let's look at what I mean by that. So here's our blob, our pancake, and the blue line, let's say, represents the knife. So right at the edge of the pancake of the red there, that's going to be 0% of the pancake. And then as we make it all the way across, right, you're going to have 100% of the pancake. And so as you move that knife, as that blue line is moving, right, notice that it's moving in a continuous fashion. So it's giving us the area in a continuous way. So is there at some point that I could pause the knife moving and I'm going to get half of the pancake? Yes. And so that's also the idea of the intermediate value theorem. As long as you have a continuous function, then every value in between on a closed interval is attained. Those were a little more fun things with the intermediate value theorem. Now, things that you'll see in your homework will be more things like this. So use the intermediate value theorem to show that this function has a solution on the interval 0, 3. All right, so then in order to do something like this, it says use the intermediate value theorem. So one of the things that we're going to want to do is make sure the conditions of the intermediate value theorem are met. And so I really recommend that you find a 3x5 note card and start putting important theorems on there. And so like in the previous videos, we were doing the continuity checklist, put that on a 3x5 note card. Intermediate value theorem, put that in a 3x5 note card. As we go through more calculus concepts, I'll prompt you of things that you need to have so that you memorize them and know the conditions. So the conditions of the intermediate value theorem are that we have to have a function that is continuous on a closed interval. So continuous on AB, and what else has to happen? So let's go here. Suppose f of x is continuous on a closed interval AB and L is a number between f of A and f of B, then there's at least one number C satisfying f of C equals L. So f of x is continuous on AB, and we have f of A is less than L less than f of B, and it just says L is a number in between, right? So it could be or f of B less than L less than f of a, depending on whether you have an increasing or a decreasing function. So it's just L has to be a value in between. Then IVT, the intermediate value theorem, says there is a C in AB, open interval AB, so not one of the endpoints, such that f of C is equal to L. So what do we need to do then in order to solve this problem? We need to get our hands on an AB. So find a closed interval AB where our function is continuous, which means what function? So we also need to find a function. So we need a function, and then we need to find an interval. So based on this, I'm going to say, well, let's let the function be the thing on the other side of 0. Let that be f of x. So I'm going to say here, let f of x equal negative x to the 5th minus 4x squared plus 2x plus 5. And I'm going to start with the interval that was given to me. So show that it has a solution on the interval a0, 3. So let AB be the interval 0, 3. Is the function continuous on that interval? Right, I have to, in order to use the intermediate value theorem, I have to say that f of x is continuous on a closed interval. I have a function, I have a closed interval. I need to make the argument that my function is continuous on that closed interval. Well, is it continuous on that? Yes. Right, f of x is a polynomial, so it's continuous on the entire real line. So if it's continuous on the entire real line, of course it's going to be continuous on a closed interval. So I can say it's continuous on that closed interval, so it's continuous on the entire real line. So now I have the first condition of the intermediate value theorem. Now I need to establish that L is a number between f of a and f of b. What's my L in here? I want f of x to equal 0. So that is going to be my L. So L is 0. So keeping in mind that L is 0, let's make the relationship. So I want f of a, let me say, we want L to be between f of a and f of b. I'm going to try to avoid the inequalities because I don't know which way it's going, right? So AB is 0, 3. So f of 0, what is f of 0? We'll plug it into the function. So when I plug in 0, I'm going to get 0, 0, 0. I'm going to get 5. So f of 0 is 5. And then what about f of 3? Right, 0, 3. So let's see. Oh, that's going to be, let's plug that in. So negative 3 to the 5th and then minus 4x squared. So 3 squared plus 2x. So 2 times 3 plus 5. So because that's my f of x. And so do this on your calculator and what do we get? So notice that the negative is outside of the parentheses, right? Because my function is negative x to the 5th. So think about that as negative 1 times x to the 5th. And x is 3. So this is just negative 1 times 3 to the 5th. So I'm going to have negative 243 and then minus, not plus, minus 4 times 9 plus 6 plus 5. And what do we get? So I got negative 268 when we put in our calculator. So let's see. So we have so far, what do we have? We have that f of x is continuous on the interval 0, 3. And we also have that 0 or L, right, is between f of 3, which is negative 268, and f of 0, which is positive 5. So notice that 0 is a number that is between a negative and a positive, so that definitely works. Therefore, by the intermediate value theorem, there is a C in the interval, open interval 0, 3, such that f of C is equal to 0, right? Or L is 0. So that's what the intermediate value theorem says. Where is our definition? If f is continuous on a closed interval and L is a number between f of A and f of B, then there's at least one number in that AB interval such that f of C is equal to L. So that's what we just found. So our f of x, right, we want that equation to be 0. That's what it means to have a solution. So we let that be f of x. We want it to be 0, so we let that be our L. And now, in order to use the intermediate value theorem, we need to make sure that we have the conditions of the intermediate value theorem satisfied. So what does it mean to satisfy the conditions? F of x is continuous on the closed interval, and 0 is a number between those function values. And so that's what we did here. Right? We established that f of x is continuous because f of x is a polynomial, so it's continuous on the entire real line. So therefore, it's continuous on a closed interval of the entire real line. And we find the values of 0 and 3 of our endpoints. And we see that one is positive and one is negative. So since the function is continuous and you go from a negative to a positive, what has to happen? You have to go through 0 in there. So therefore, there is a value such that we have a solution. So what this means is that there is a C in 0, 3 such that negative C cubed minus 4C squared plus 2 times C plus 5 is equal to 0. So there's a number between 0 and 3 where when you plug it into the function, you get 0, meaning C is a solution to the equation. So that's one way that we can use the intermediate value theorem. I will record another example using a proof by contradiction that oftentimes comes up with using the intermediate value theorem. Email me if you have any questions. The intermediate value theorem is one of those that is a bit tricky, but I just want to emphasize, as long as you're establishing the conditions of the intermediate value theorem, right? It's continuous in a closed interval, and that you have a number L between your function values, then you can use the intermediate value theorem. But the crucial thing is establishing that condition, right? So like here, this was my function. So I have to make the statement, this function is continuous on the closed interval. So that is the big step. All right, email me if you have any questions.